But in any case, as Henrique kindly introduced me, I'm at Catholic University of Paraná now. And I was before joining Curitiba, which is my hometown, I was in Rio for 8 years, yeah. So yeah, I'm just talking about my whole trajectory in a while. So today's agenda, so I divided into 3 parts, okay? So the first part would be some preliminaries, or I'm going to introduce myself and talk a little bit about some basic stuff so that we have like a common ground to start discussing. What we have like for the second part, which is prior work that I have developed together with the students. And also in the third part, I would call it the future work or future/ongoing work, including that the preliminary results that we're getting now with this collaboration. So I arrived in Erlangen for in the past 3 weeks I've been here. So yeah, so we're working together, and I'm be very happy to show you the results that we got thus far, okay? So yeah, so since, as I told you, if you can locate in the map, Brazil, Curitiba is in the very south of Brazil, yeah? And its closest capital to São Paulo is like 400 kilometers away from São Paulo, and also 900 kilometers away from Rio, yeah? So if you can locate in the map, it's more or less the closest capital from São Paulo. This is like the southern region to Brazil, yeah. And yeah, prior to joining PUC Paraná, I was, as I mentioned, in PUC Rio. So I was also a professor at PUC Rio in the Department of Mechanical Engineering for about 8 years. And prior to that, I was also working, before I finished my PhD, I was also working in some companies. So I worked for a couple of years at IBM Research. They had a lab in Rio, and that's the reason why I went to Rio in the first place, yeah. And I also worked in Embraer. Maybe some of you know this company because it's like the Brazilian Airbus. It's the third largest aircraft manufacturer. So there's Airbus, Boeing, and the very distant third place is Embraer. And that was a very nice time. Like I was working as an engineer, so I was doing like a part-time for my PhD, which was not really a part-time. I had to work on my PhD and work at the same time at Embraer as an engineer. So I did like for 2 to 3 years, more or less. And some students come to me and ask, okay, do you think it's possible to do a PhD and work at the same time? I mean, in the industry? I said it is possible, but it hurts a little bit, you know? It's a lot of things to manage. And prior to that, as Henrique also said, I was at ZF in Friedrichshafen, which is on the other side of the lake, opposite to Constance. And my broad research interests are first, system identification, which we're going to discuss in deep today. Also advanced controls, mostly MPC, model predicted control, and applied machine learning, yeah? So the reason I'm here today, and I'm going to state like a very broad goal for this visit, and then we're going to go into details in the future, in the next slides. But the ERC project that the Professor Henrique has, we can apply, as Brazilians, we can apply for funding to come and visit, okay? And then we submitted a proposal, which was approved in November, late November, more or less. In December, it got running, and then I managed to come in January this year. It was a bit of a rush well, you're familiar with managing grants and stuff, so yeah. So you must be aware that traveling like in this distance for 1 month, organizing everything for a month, it was really a challenge. But with the help of Maureen and all the other staff from FAU, we were able to do that. So we divided this proposal into 4 stages. The first stage would be to perform hybrid modeling. So prior to that, in November, I did a couple of experiments in PUC Paraná. And what we are doing here, and also synergistically with the project from Professor Henrique, was to propose a hybrid modeling paradigm. So hybrid means we're mixing physical models, which have been running for a long time, right? And black box models, which are somewhat newer when we talk about simulation, if compared to physical models. And we want to establish what would be the best way to combine all those approaches, if it is possible to do that after all. And then in stage 2, we also interested in modeling using multimodal information. And this means that we're using not only proprioceptive data from the process, but also video, external information, okay? We tried this before, it's incredibly hard. But yeah, we're trying it again, yeah. And the third part would be to use these hybrid models to build control laws which are revolving in the model predictive control philosophy. And we want to do that in approximate fashion, because then we can run this on real time using real world hardware, yeah? And we're going to detail this too. And then on stage 4, which would be a moonshot, I would say, would be to use or to interact with the control system in a much higher level. So if we're able to simulate the system using images, maybe we can even plug a ChatGPT or whatever model to imagine or to generate an image, for example, when we say, okay, I want this bottle to be in this place, and we can use this image of the bottle in such a place for a robot so that it can receive the commands in a more natural way when we are interacting with this control system. Yeah, this is why I call it a moonshot, because this should be very difficult. And before proceeding, I wanted to give a shout out to the former students that I had the chance or the privilege to supervise in the past 8 years, more or less. So many of them are working now in the universities in Brazil, or they headed to the US for their PhDs. Maybe they're coming here to Erlangen in the future too, to work with Professor Henrique. And some others are also working at companies like IBM, Petrobras, Volvo, Boeing, Embraer, and the like. So yeah, so I just wanted to acknowledge that their work is also, I mean, I'm presenting this, but it somewhat belongs to them too.
This is in Brazil, companies like TikTok or...
No, this guy went to California. Daniel is in California. Mateus is also in California, he's in Stanford. And the rest should be in Brazil. Yeah, IBM in Brazil. This one is a Norwegian company. Yeah, but I'm not sure if she's in Norway now or in Brazil. Yeah. Yeah, so let's talk a little bit.
Company on oil industry?
Yeah, that is an oil company industry, yeah. So now, as I mentioned, we're dividing this talk into 3 parts, right? So the first part would be like the introductory part, where I'm going to state what is system identification, for example. So if you locate the control field here, so everything that is in controls, the majority, I would say, is model-based control, right? So, for example, if you want to design a controller, you depart from the assumption that you have a physical model, that you can quantify things, and then you can do design, okay? So that's what's used mostly for making aircrafts fly, to trains, to brake, and whichever circumstances that are critical, because you have to build a physical model. And once you're running the control system, which typically is related to a critical operation, like a rocket, for example, or an aircraft, you have to be able to substantiate your design decisions, right? So as an engineer, you want to use a model because it helps to quantify, and it will also be possible to justify your decisions, right, as an engineer. And inside model-based control, there is system identification, which is the field within control systems that is related to building mathematical models or models from purely data that we're using, okay? So let me give you an example. What is system identification? So say, for example, that your boss comes to you and say, okay, you have to design a controller for this system, okay? You cannot tell him, okay, boss, I will just do that if you handle me a transfer function for the system. You have to somehow build this transfer function yourself. So if you're into control and model-based control, which is most commonly found, you need to do something or something related to modeling in the end of the day. So what you can do, if you want to use data, at some point on the product development phases, you'll be able to do that. You can ask a question to the system. What is asking a question to a physical system? You just apply an input or an excitation signal to that, which you consider to be your excitation signal that will be devoted to, which will be designed by the control law itself, okay? So the input we can, for example, this is an example of the data set we're using right now. You can use, for example, you can define the amplitude of the data set and the frequency range that is going to be excited in order to acquire the data. So in this example, we just did a multi-sign excitation signal, which we designed using Fourier coefficients, and then we invert it. For example, this is one way of doing that with random phase. There are many types of ways of designing a signal such like that. And then once you ask the question, the system is going to reply to you, right? So you can do measurements, right? So this is the result of the measurement that we did. And when I was doing those slides, I realized that there is a line here, somewhat constant in 60 hertz. Can you imagine why this is so? In the measurement? That's because our power lines in Brazil are 60 hertz. So when we were measuring that, it was disturbed by the power lines, you know. Of course, we can filter that out, it's not a problem. So once you have the input and output data, and this means that you're asking a question to the system, it is replying to you, you can do what we call identification, right? So you're using basically input and output data, and throughout the process of identification, you get, in the end of the day, if everything goes well, a model that is going to be important for an analysis tool. So everything departs from building a model, and that's how we do using real-world data, okay? Anyone wants to comment on this? It's fine, system identification? So I'll give you another example. So there is a student, a master's student, that is building a two-wheeled inverted pendulum robot. So imagine that you have two legs. All the structure is 3D printed, sorry. And we have here two DC motors, which command the wheels of the robot. And we also have 4 servos there that are like the hips of the robot. So it can stretch and control the position of the legs. So in this robot, those 2 motors are the same. I mean, they are the same model, but they behave differently, okay? So how do we control a robot like this? Using system identification and controls. So the first step would be to control the velocity of the wheels of this robot. And how can we do that? We can ask the question, who are you to the motor? And how can we do that? The simplest thing that I can imagine is applying a step function to the voltage of the motor. And what happens? It starts to spin, okay? And this velocity is measured through the optical encoders. And we can use this response in order to quantify or model this motor, yeah? So yeah, this is very simple. I mean, this is a first-order system, right? But even though it is very useful because then we can build controllers. So what I'm showing you here is the result of the control of this simple DC motor. So what we have here is a reference signal in black lines. And the red one is the resulting velocity that is measured. Okay, so even though the signal is noisy, the result is pretty decent. I mean, we're only using a transfer function with 2 parameters, with a gain and a time constant, and that's it. And then we do the design offline, and we implement it in the real robot, okay? And we can see also here from the excitation signals they're used to command the system, that the system is nonlinear, right? Because for the same changing in the reference, the inputs are different. If the system were to be linear, they would be exactly the same for all step changes. This means that our model here is invalid or that is not useful? No, it was good. So there is a matter of purpose in modeling too. I mean, what is the best modeling paradigm. So I don't believe in best modeling paradigm or something like this. But in any case, we have basically two opposing sides when we talk about modeling paradigms and system identification. The first would be the white box approach, where we go and measure, okay, what is the mass of this bottle? What is the friction parameter from the bottle to the table? So we can measure that. So if we are able to build a model like measuring parameters like that, that would be a white box model, okay? And on the opposite side, there is the black box modeling paradigm. So the black box modeling paradigm would be not using physics at all. I mean, we're only using data in the end of the day. What to me, I mean, after like some 20 years doing system identification, I would say that those white box or black box modeling paradigms, they don't exist, really, because you're always using some knowledge about the system, and you're always using some data at some point. So they're more like a conceptual part of the modeling process, and they depend also on who is building the model. So if I'm building a model and I know how to model bottles, it's going to be, or motors, as we just showed, it's going to be a different model from someone that doesn't know how to do that, but is savvy with data, for example. What's the best approach? I don't know, it depends, right? So there's a quote here that I like very much from Professor Jung. He's also a researcher in system identification, that our acceptance of models should be guided by usefulness rather than truth. And I genuinely believe in that, yeah. Because if you use physics, there will always be something that you'll be able to model more and more and more and more. But the bad news is that your time costs money, right? So if you're going to build a model, okay, you can spend your whole life modeling a DC motor. Is it going to improve controls? I don't know. I don't know. So it should be, and I agree with that, the modeling paradigm should be guided by usefulness in the end of the day. So what kind of models do we expect to get from system identification? So yeah, so this is something you should be acquainted to. State space models, for example, we can get from system identification. Yes, we can. Difference equations like transfer function models in the Z transform, we can get that too, yeah? And the nonlinear counterparts, right? We can also get nonlinear state space models and nonlinear models that model the relation from the input to the output. We can also do that, yeah? And yeah, so in this context, we also discuss some hybrid modeling paradigms, okay? So when I was doing those slides, I just found a very recent paper from Mukherjee and Zavala, and they are trying to categorize what kind of hybrid models that we can get. I mean, once we have, for example, white box models and black box models, as I just showed you, how can we hybridize them, yeah? So that we can get a better result. And I'm going to show you in the next slides, some examples on this, on some prior work on this, and also how this has impacted our work so far here in Erlangen. Yeah? So how can we do that? So maybe in letter A, you're adapting your input function so that it's cleaner, in a sense, for the physical model, for example. Or maybe the physical model is going to be adjusted by the black box model. Or maybe, and this is something that we tried many times, and it tends to work very well, is to use the black box model to model the residuals of the physical model, yeah? And you can also try some more fancy configurations as well. Yeah, I'm going to show you also an example of this for modeling flexible manipulators. Well, talking about system identification, I'd also like to introduce you. So I'm lecturing a graduate course on system identification for some years now. And I translated all the code and all the information for this kind of I don't know, maybe a website or book, I don't know, so that you can access if you wish. So we have background material with cooked examples, numerical examples, and we also have activities with real-world data. So yeah, so we have here also case studies, and there are numerous examples using real-world case studies here for the modeling part. Yeah. Okay, so that was the first part. I hope I didn't lose you thus far. And now I'm going to briefly discuss our prior work on that, and mostly related to hybrid modeling. Okay, so how can hybrid modeling be used synergistically in the system identification domain? Yeah. So the first example I'm going to show you is a paper by Ingrid. She did her PhD in PUC-Rio. She finished maybe last year or something, or 24, I think she finished. And she was actually supervised mostly by Hans, but as he was an emeritus professor, he needed a co-supervisor, and then he called me. And then, yeah, we also managed to work very well. And yeah, so the whole problem here, so as in Rio, there are many oil companies. There are many applications that are oil companies oriented in a sense, because there's a tendency of being funding available for that. So there is like, how can I say, an atmosphere among the departments to work on applications in this field. Me, myself, I never thought of working on this, but when I arrived there, they had those applications, and I thought they were, in the end, very interesting. So, for example, here, we have a benchtop that was built in order to emulate what happens in a drilling system. So in a drilling system, you have a very long structure, very slender structure, that you apply a torque, and this structure, in the end, has a drill bit. And this drill bit is used to make the hole in the ground so that they can find oil, right? So what Ingrid did with other students, she built a benchtop in the lab in order to emulate what happens, or situations that are similar to those that are found in the field, yeah? So what she did here, there is a DC motor here where she applies a voltage and a torque. And those inertias are connected to aluminum rods that are very slender, if you compare to the inertias. And there are also braking mechanisms, that you can use in order to apply a resistive torque to the inertias. So this is used to emulate somehow what happens in the drill bit, there in the bottom of the sea, yeah? So she built a dynamical model for this. It's basically a state space model. It would be linear, not if we didn't consider TF like a nonlinear friction model. So she tried many different types of friction models. And what happens is that the results were much improved when she added another layer of complexity to this model, which would be something similar that we mentioned about the residual compensation, right, of the physical model, yeah? So what she did is she considered a dynamic model that is built from the gray box model firstly, and then the black box model was built in order to compensate the residuals from this gray box model. So here you see the response of the physical model in a very challenging situation to simulate, which is when the inertias have zero velocity. So this happens when on the operation of the benchtop, the resistive torque is greater than that of the torque that is being applied to the inertia. So what happens in this situation is that the inertia stops, and this is very difficult to model. As we can see here, I mean, we're even able to emulate a little bit of this situation. But once we add another layer of complexity, the results improve a lot with respect to this situation. And this is important because when the inertias are stopped and we are applying a torque to the motor, what happens is that in this bin, which is in the application side, the structure of the drilling string, it accumulates energy. So if there is a torque being applied there and this inertia is stopped, the rod is accumulating energy. And once it releases this energy, it can be catastrophic. So representing this phenomena is very important. Yeah. So this is, I think that this was the first paper that we wrote on this, on hybridizing physical models with black box models. Yeah, from English. And then a bit time later, there were also other students interested in robotics. So Daniel finished his PhD a couple of years back too, Felipe too, and Antonio was a brilliant master student. Yeah. And this was a work that me and Marco, who's into robotics, developed together, so he also could supervise the other students. So the goal here was pretty much the same as in the paper before. We're trying to build physical models that have a good matching between the data, but also can be improved with the hybrid approach. So this case study is something that also, it's very hard to model physically, and I'm going to explain you why. So in this case, we have a flexible joint. Okay, I'm going to point you with the mouse here. Yeah. And in this case, what happens is that we have a rubber here. What you see here in black is a rubber. And this inner part is connected to the axis of the motor. Okay? And this outer part is connected to the end effector. Okay? So what happens in this case, in this situation, is that we can control not only the position of the end effector, but also the load that is applying and exerting in the environment. So for example, if you have a robot that is interacting with a human, it is important that you control also the load that is applying to the end effector, right? So that's what we did here. We built this flexible joint, but the whole problem was, okay, now we have a flexible joint, but how does it behave? How can we simulate it? And it's very difficult to model this. I mean, we started with the simplest model that we can imagine, which would be a simple linear relation. I mean, we're just modeling it as a spring, okay? And then we are adding here also nonlinear friction, and the nonlinear friction models are very similar to those that we used in the paper from English. And here, most interestingly, is that the architecture that we found out to improve the results, finally improve the results, or that improved the most the results, was a structure like this. We have a gray box model and a neural network that corrects it in order to add the residual to the response of the gray box model. Okay? So, of course, this is non-trivial, and we tried many different possibilities until we came to this final best architecture for this paper, yeah. So here you can see the linear model. I mean, from the physical model perspective, the linear model already have a very good matching for these data sets. I mean, 0.89 for the R2 is pretty decent. But it was improved by the nonlinear models. I mean, the Lugre model, Lugre fictional model, came up to 0.94, yeah? So once we added the black box to this hybrid modeling approach, it was able to reduce significantly the MSE by the end of the day, yeah? So yeah, so that was this result that we got from this paper. And it's also interesting here because what is the best hybrid architecture? This is, I mean, each time that we try it is different. I mean, at least this is my experience thus far. And this is another paper that we did. So this is how it looks like when we are exciting or we are using this flexible joint. And this was, yeah, you can see Antonio's foot moving there. But in any case, here we are applying a torque to the motor and we are recording the position. And why so? Because we were interested in starting to model it using also video information. So that's how we found out that it's very difficult to do that. Building models from video is is much more difficult, yeah. And this is also relevant to our proposal here, because we'll also try to do that with other case study here, in a more controlled environment, I would say. Yeah, so how we did the hybrid modeling here, no, not the hybrid modeling, but the multimodal system identification here. We're using some off-the-shelf models used for ImageNet competition or the like, in order to extract the kinematic information, yeah? So from this kinematic information, we have the physical models that we can also try to build on this, yeah. So takeaways or conclusions from our prior work and how it affects what we're going to discuss in the third and last part of the talk would be that the hybrid architectures always change. I mean, we have other papers on this, and each time that we try it, I still don't know why, but the architectures from hybrid modeling perspective, they vary on which are the best for each application, yeah? So I think it would be good to understand why this happens, and there should be some results that we can, since it improves so much the prediction power, I think it would be a good idea to establish what are the best approaches for each application, yeah? And multimodal modeling seems to be very difficult, yeah. So those are the takeaways from our prior work, yeah. So yeah, so now for the third part, anyone wants to comment anything so far? We're good? Yeah? So yeah, so the third part, before we go to lunch, before and last, yeah, the third and last part of the talk would be the future and ongoing work. So this will be mostly related to our joint project, the ERC CNPQ project with Professor Henrique. And first, I will tell you about the case study that we did the acquisitions, and then we are going to detail what are the objects and goals for the short term. So maybe you also find like you would like to work on multimodal hybrid model learning, maybe, yeah. You'll be very welcome to join us in this project, okay? So the case study, the motivation for the case study would be to start with something simple, right? This was the most governing factor on choosing this benchmark. Starting simple, but still with difficult and interesting questions to answer, okay? So this case study was acquired from the ball and bean experiment. I don't know, this is very classic control application. It is also a motivation for using this, but it's basically a bean, okay, that you put a ball on top of it, and then the goal is to control the position of the ball inside this bean. And this is a very interesting problem from the controls perspective, because it teaches the students how to control a system that's not stable. So what happens if you, for example, if you have the bean with an angle that is non-zero, if you put the ball here, what happens to the position of the ball? It increases to infinity, right? So if you have a step function, the output goes to infinity. This is the definition of unstable system, right? So this is interesting because of that. The double integrator, which ends up to be the dynamics of the ball, is also found in numerous applications. Numerous. I mean, there are countless applications that you can define your model as a double integrator, like the lateral dynamics of vehicles, the vertical dynamics in drones, for example, it's a double integrator. So anything that has force equals to mass times acceleration is, in the end, something similar to a double integrator, yeah? So this is a compelling example for this reason, yeah? And what we're trying to model here is not, we didn't even put the ball inside, on top of the beam. We're just modeling the position of the beam when it is controlled by the voltage that we applied to the motor. So the mechanism in this system is you apply a voltage to the motor. The axis of the motor is here, and we have a cam follower system that transfer this torque that is applied to the motor to the beam. And this is done, I mean, we could, it was a design choice, we could put the motor in the beam directly, but then the beam would be able to turn like 360 degrees, which is not a good idea to, to put in a control lab because, yeah, you can imagine what would happen, yeah. And when we have the came follower like this, the position of the beam is constricted to a certain extent, yeah. So this is a very clever design for this specific case study. And here, this is a top picture. I'm just going to show you a video in the next slide. But here we can see the position of the beam is measured by a potentiometer. The potentiometer is basically a resistor that changes its value according to the position, yeah. And here you can also see a slight part of the beam here, okay? Okay, so yeah, here I'm explaining some motivations. Here you can see also the beam in operation, yeah. So this is a sequence of steps. I'm sending, this is in closed loop, yeah. So I'm sending here commands of reference of position for the beam. And that's the measurement that you're seeing there, okay? So yeah, so the motivation, I already talked about this. And yeah, the data sets are fully available online. If you wish to use it, be free to do that, whatever you like. And we developed here, when I came to Erlangen, with the help of the others, some helper functions to load all the data, so it's very easy to do that. And also the video data that I'm going to show you afterwards. So what kind of data sets or questions that I'm doing to this system? So we have 3 types of data sets. The first would be a multi-sign, which was the same that I discussed in the start of the talk. So in this case, I defined a range of frequency. I think it was 5 hertz, if I'm not mistaken. I'm not sure. And an amplitude of operation that the beam would not start to pass to a, so let me show you this picture, maybe it's easier to explain like this. I restrain the amplitude of the voltage so that the came follower is always on this side. So the effect of the nonlinearity of the geometry is not present in this data, yeah? So I define an amplitude for the multi-side and also a frequency range. And I did this 2 times. I mean, 2 realizations of this same data set, which is random, because the phases are random here. And that's how the system replied to me. Yeah, so I'm asking a question, who are you? And it's replying to me. And I also did for evaluating how the model performs in something that is more similar to the operation of the system. I also did the sequence of steps for acquiring the signal. And also another signal that is also interesting to use is the swept sign, which increases the frequency linearly for time. And it's mostly used to validating the model. Yeah. So that's the data sets that we have. So we have this and also the corresponding video that I'm going to show you afterwards. Yeah. So yeah, so this slide was the same that I mentioned in the start of the talk. So I'm going to revisit all these topics. So the first stage would be the hybrid modeling part, okay? So how can we improve the simulation capability using the data that we have? Not using video still, because stage 2 will be to perform the same thing, but using multimodal information. And then the third stage will be to use approximate MPC, or model predictive control. So we want to establish what's the impact of hybrid modeling in model predictive control. My hypothesis is that it's going to impact positively because the predictions are much better and the control laws totally depend on the model that you build. Yeah? And the stage 4 would be the moonshot that I showed, that we discussed before, would be to use a higher level control interface with the control system. I mean, we're going to use ChatGPT and ask, okay, so make the beam do something that is more meaningful and more natural language style to interact with the system. So yeah, So now I'm going to present to you, Henrique, I'm good? Time for the minute? Yeah. So now I'm going to present you some preliminary results, yeah, from the work that we've been doing here. Please, a shout out to the Spanish team. Thanks for your help, yeah. So for this system, we first established a physical model, yeah. And then we are now comparing to a black box and a hybrid modeling alternative. Pretty much in the lines of the prior work that we already did, yeah. So let's see how it develops. So the first linear model, I assume you're familiar with state space equations, but in any case, we here established a linear model, which is basically a spring with a preload. So this delta here is the preload of the spring, which is keeping the beam attached to the cam follower. Yeah. We have the how can I say, the spring constant. We also have viscous friction. In here we also have a torque constant. Okay, so this tau is translating the voltage command to a torque that we can translate to the mechanical world. Yeah. Of course, there are a lot of simplifications here because we are not even including the dynamics of the electromechanical motor. But this is the very first version, yeah? So let's see how it does. And for the nonlinear physical model, we are changing this viscous friction model to a more elaborate nonlinear friction model, yeah? For the full black box, we're using, in the state space equation, a full black box approach. That means that the state or the transition equation is going to be learned throughout the process entirely. And the hybrid approach is using part of the physical model and part of the residual model. Okay? Well, I mean, the residual model is going to be all that the physical model is not able to represent in this transition equation is going to be captured, ideally, we hope so, by the black box model. Yeah. So some details about the results that I'm going to show you is that those models typically use free-run simulations for the whole data set. So it was taking like ages to do that because the data set is a bit, maybe, I don't know, it's a bit long. So what we used, instead of using one step ahead, which would be the other opposite, right? Only use the initial condition and check what is the next prediction. We're using case steps rollouts for this data set, yeah? So this was a bit tricky to implement because of the time dependence of the input and output variables. But it was no match for the Spanish team because they did it like this. And the loss function is calculated only for the position. So we're only comparing the first state because that's what we're measuring. We're not measuring the velocity. We're just estimating the velocity in order to use the initial conditions and calculate the rollouts throughout the calculation of the loss functions, okay? So yeah, so the first test protocol that we did, and here you can see all the models in this column, and on the other columns is the result of the modeling for each of the data sets that we have. So the first try we did was to use the first multi-sign signal to train. I mean, we used it entirely. And we are testing against the other data sets that we have available, yeah? So what you can see here is that I highlighted here all the data sets that are broadband signals, meaning that they contain more or less the same information. So this data set is a multi-sign data set. This is also a multi-sign data set. And this is a swept sign data set, which also contains the same frequency range and the same amplitude. So in this condition, the hybrid models performed very, very good. I mean, they were able to improve all the physical models or even the black box models, and also in the multi-sign case and also in the swept sign case. In the random steps, which is here, all models perform somewhat poorly, yeah? So then I look at this result and then I thought, okay, yeah, maybe the information in the data set is not enough, yeah? So what can we do with the data set that we have? Because I'm here, I'm not in Brazil, I cannot do any experiment. What can we do? We can try to figure out another test protocol in order to try to test other things. So what we did here, we're using a lot more data now. And we are using 50% train and test protocol for verifying the quality of the models. Yeah. So now we are using all data sets except the swept sign, which I'm going to explain a little bit why we didn't use this for training. We're using all data sets but the swept sign in order to build a model. And what I'm showing you here is the test results of the remaining 50% of each of those data sets. So in this case, the hybrid modeling paradigm performed better than any other approach. And this is somewhat encouraging for and confirming our prior results also on other topics, that the black box modeling can also be used synergistically with the physical models. I mean, we should not throw one away, each of the options, but instead we can use them synergistically together, right? So the reason why we didn't use the swept sign signal is because if we separated or divided into 50%, only half of the frequency range would be constant, it would be present in the training data set, and the rest would be in the test data set. So as we had enough data, we just didn't use it, okay? So future work. We're going to run some extensive hyperparameter search in order to define and establish more conclusive allusions here about the results. There's also the possibility to reiterate the physical models. We can always improve the physical models. Yeah. And another direction that we still have to, I don't know how we're going to solve this, but how can we establish if the information on the data sets is enough for building the models? Yeah. So this is our future work. So for stage 2, we have multimodal hybrid model learning. So now we're going to use the images. I'm going to rush a little bit on the future work because we're running out of time, and then you have also time to comment on the talk. We're going to basically use now multimodal information to build the physical models. Yeah. And for this, I spent a lot of time just to get those images synchronized with the videos. Yeah. It took me a long time to do this. You wouldn't believe it. But in any case, the stage 3 would be to use the approximate MPC. So if you're familiar with MPC, MPC can be solved at each sampling interval on finding the optimal control sequence for a receding horizon window, right? That is moving through time. So we solve at each timestamp, we solve an optimization problem in order to define this optimal control sequence. We take the very first sample of the control sequence, apply to the system, and then we reiterate it in the next time as well. Yeah. So this, as you can imagine, is very expensive to do in real time. So that's why we are proposing to use, and this is not new. I mean, the first time that I saw, or the first work that I know that used this approach on approximating MPC is from '96 from Camacho, which is also from Spain. So he used this approximate MPC idea that I'm going to tell you about now for controlling a mobile robot with his student. Yeah. And how can we approximate the MPC? There are many ways of running MPC fast on embedded computers. Maybe one that we can easily generate with the models and the tools that we have thus far would be to face this optimization problem as a mapping from the measurements and the references to the control actions. So the optimization problem is basically doing this, right? It takes the references, the current state or the output, and calculates the input that should be generated, right? So if we solve, we have the models, we have the MPC, we have everything. We can solve this optimization problem for the whole control envelope, or as good as we can. We can solve for this whole envelope, and then we can try to build an approximation to this from this mapping. Yeah, we can use neural networks to do this as well. Yeah, and this is in fact been used like in very recent work from last year at ICRA, which is the International Conference on Robotics and Automation. Some German researchers have done this in this mini wheelbot, which is a very interesting paper. I recommend you to take a look afterwards. But that's how they implement it in cheap hardware. I mean, not cheap in the sense of the price, but or constrained hardware resources. That's how you can implement it, because the inference for the neural network is very fast if you compare to an optimization problem, right? And the higher level command interface would be the moonshot that we discussed, would be to use some imagination or models that we can like, okay, so generate an image for me of the bean at 45 degrees, and then we can use this as a reference for the control system. Yeah, this should be difficult, but yeah, we'll try anyways. Yeah, and that was my talk for today, and thank you for your attention.